seems like spring must be in the air. Birds are chirping, the students are arriving late. It does feel pretty nice out. I will open the door unless anyone has an objection. A little cooler air. Feels a little, I don't know, it's nice. Dry. First thing, apparently I made a typo of sorts on the homework, and apparently it doesn't show up, or it didn't. So if you wanted to do the homework and you tried and you found it wasn't there, I'm sorry. It's there now, and it's obviously not due today. It's due when you turn it in. There's not going to be it's not going to be a required homework tonight, so you can turn it on Thursday or next week, it'll be fine, if you want to do it. Yeah. So I can't really ask if you have any questions about it. A little information on the quiz. The grades, the scores were 98 to 68, average 85.5, and the median score was 84. Those who like to know these things. There was a range of problems. One problem, after I separated like the papers that got it right, there were about 8 or 9 different answers to problems, and I had to go through each. I think just about every one, it was really a different thing. So I had to figure out how to score those. Some obviously. I treat, like you add 1 and 1 and you get 3. I don't really count that too badly because I don't care if you can add 1 and 1. But there was one problem I saw on a number of people's exams, and I actually understand that a little far out from where you learned it, this might be confusing, but it had to do with what you do when you're raising something to an exponent. And this is actually from one of the problems. Here we have e to the theta over 2 squared. And the long way is to say, well, that's e to the theta times e to the theta over 2, e to the theta over 2. But we add the exponents and we get this. Or you can just multiply 2 times this. Again, real basic, but enough that you got it wrong that I think it's probably more in this context it was confusing. I think if I said this, I think everybody would immediately go, oh, that must be 6. 5 to the 6. So. Okay, just, again, I don't count those as badly as errors where it shows you didn't really understand something we were trying to learn here. Are there questions about any of the quiz problems? Any that you'd like me to go over? I guess I'll mention this also. Sometimes it didn't hurt and sometimes it did. But when I put on a problem exactly, if after you're all done showing me exactly what the answer is, you run it through your calculator and give me an approximation, I just cross it off and say, okay, and I don't take anything off for that. But if you don't, if you don't give me the exact answer at this point, I don't know what to say. It's not what I wanted. So, okay. All right. No questions. Okay.
Okay.
Yeah.
Can you do number 3?
3. Okay. This is the one where everything went wrong. It wasn't really clear on paper on everyone's, and some people had some trouble misunderstanding it. So, first of all, let me just kind of draw a rough sketch of what the graph looked like. It would keep going. And I say, bounded by the polar equation, r equals theta over 2. If anybody really held my feet to the fire, sure, you can say it's infinite. This keeps going and keeps getting bounded, but nobody went there. I think everybody kind of looked at this in the small picture, which is what I intended. And the real question here is, what are the limits? What are the theta limits? So they tell you bounded by this axis and above it. And so what I'm really looking for is going from this point to this point. So how do you find that? Well, there's a couple ways. You could look at it by inspection and realize that theta is going like this. It's going from 0 to pi. But if you wanted a straightforward way to do it, you would have to look at the equation for y. All right, y is r cosine theta, and theta, r is, I guess I should put this up, r equals e to the theta over 2. This is e to the theta 2 cosine theta, and we want to know where y is 0. Well, this is always positive, so this just reduces to cosine theta equals 0. I think I'm about to do something wrong. I'm sorry. Yeah, it's obviously y equals r sine theta. So where is sine theta equals 0? Well, obviously 0 and pi. Now we need that formula which says that when we're integrating across theta on something described in a polar format, we integrate r squared over 2 d theta. And that simplifies to e theta over 2 squared over 2 d theta, which just becomes 1/2 0 to pi theta. And that, of course, very easy to integrate. And what does that give us? 1/2 e to the pi minus e to the 0, which is 1. So that would be the answer. That clear? Okay, any other problems you want me to go over? Okay. Just leave this up here for now. So we're going to do a few things today. First thing we're going to do is look at something called a direction field. This class has gotten me more than anything I've done in the last 10 years thinking about the relationship of technology to what we learn. And I mean, the prototypical question is, well, why should you learn how to add, subtract, multiply, and divide by hand when you have a calculator? And in grammar school. And it turns out that it's mostly important. I mean, we don't expect people to multiply 10-digit numbers together. That's what calculators are for. But it's an important skill. And I think the same thing with finding derivatives and integrals, even though there are algebraic systems that will do it. So here we have something which is a little unique to doing differential equations, this direction field idea, which we're going to talk about. But I really feel like, well, if this is valuable, let's get a computer to do it. And if a computer can do it, just look at it and see what it is and know how it helps. And it kind of self-defeating. But anyway, here goes. So we look at this. We're going to look at this differential equation, which is y prime is equal to x plus y. And it's written right now specifically to isolate the y. The dy dx. We know that the dy dx, that's the slope at that point. And so at this origin, I've drawn in this, I drew it in incorrectly. Maybe we need a table here. So x and y prime, so here we have 0. Oh no, that's right. It's x plus y is 0. So the slope is, I've drawn a little tiny segment here. I hope it's clear, it's way too big, right? I could draw it a little smaller, and it would still be as incorrect. It's just at 0, the slope is 0. But we draw it this way to indicate that. And then we have to fill in here, which is going to take me a little while. It's going to be a little tedious. But let's give it a shot. So how about this point here, 0, 1. That'll be 1. And 1, 0. That'll be 1. And about 1, 1, that'll be 2. Let's just try those. So 0, 1, so the slope helps to know what a slope looks like for 1. Okay. Here again, the slope is 1. Oh, 1, 1. Now the slope is 2. So change in y over change in x, 2. All right, so that's where we're going with this. Let's see if we can find a way to do this a little more efficiently. So if I move up, this is 2. Here it's 1/2. Here it's 2.5. Now as I move down, now it's -1/2. It's -1. -1.5. -2. Okay. Well, it seems to me that since we've moved over 1, it's just this, right? Kind of moved over. And now here we have 1 and -1, so we're back to 0. 1 and -2 would be like -1. This is -1, so it's kind of like this. -1 and 1. Here we have 0 again. Moving up again. Now this is just move it over, right? So it's kind of 1/2, and then 1, and then 1.5, and 2. And here we have -2. So that's kind of more negatively sloped. And these just get longer and longer. All right. Here we have, I told you it was going to take a long time and it's kind of tedious. 2, even more than 2. These are getting very close to being vertical. This is 1. This is 0. Well, that's an interesting thing. Along the diagonal, what do we have? It's always 0. Okay, so 0, and that one's below 0. Goes down, -2. That's sharper. Okay. All right, so it's not the most wonderful graph. If you want to see a slightly better version of it, you look in the book. And you might want to keep in mind that how did the book create this? Did they do it by hand? No. They had a computer generate it. Again, if you can have a computer generate this this diagram, you can have a computer do a lot of neat stuff for you. Okay, so all right, so that's a direction field. It's something to look at that's trying to illustrate and give you a feel for a differential equation. A different differential equation, these little points would be, these slopes would be different. Okay, so what good is that? Well, in particular, we're interested in, today, in the differential equation with the initial condition y of 0 equals 1, which is this point here. And, actually, I think I have something wrong here. 0, these are negative. That's another thing. It's kind of anything that's long and tedious is kind of more likely to cause errors. All right. So the idea is you look at this direction field and you say, all right, well, where is it headed in this direction? Well, it's headed up this way. And here we can see they're kind of a little further along. And you can kind of get a feel for the curve in that direction. You go in this direction, well, it's going down this way, but now it's kind of leveling off and kind of moving back this way. So again, you know, we could do this at any point. We could start with any initial condition. So if we start here, looks like it's a similar shaped curve, but now it's a little off. So, you know, given the prospect of any old differential equation that you don't really understand, and you don't have a calculator handy or a computer, you might want to draw this and see how it looks and get a feel for it. So that is the trivial description, I guess. Are there any questions about this so far? Because what we're going to do now, I don't think this will take very long. You've just been presented with this, but this is a kind of these problems you have to think a little. Or maybe you'll come up with a real quick strategy that'll work. These are problems from the book. The first four are MASH. So, you know, you have a 25% chance of guessing right, but try not to guess and take a look. You can get together on this a little if you want to talk it over with your neighbor. I think that's a good idea for something like this. Or you can just be alone, we'll work on your own. It's up to you. And again, I want you to get a feel for this concept, but I hope I'm not being terribly negative about it. We're going to go on and see a little better strategy for dealing with this kind of stuff. So, okay, take a few minutes. Since I haven't done them, I guess I should look at these two. You don't have to write down a reason. We'll talk about these in a minute. And I'm actually just asking you to do the first four right now, so get done with those, look up and let me know. is almost like one of those, kind of like those puzzle intelligence tests, you know, where it's like, what's the fourth one or something? Think a little. All right, would anybody like to volunteer? Pick any match.
3 is 3.
3 is 3. Okay. Do you want to give some rationale for that?
Well, because it only has a y in the equation, it doesn't matter really what x is, it's always going to be the same for that value of y.
So if you look at 3 across, they're always the same, right? Is any other graph like that?
No.
So, okay, process of elimination. 3 is it. Very good. Does anybody want to try another one?
1 is 4.
5 is 4. Okay, can you give me a reason to suspect 5 is 4?
Linear relationship between x and y.
I'm sorry?
The linear relationship between x and y. If one is negative, the same value as the other, then it's going to be the same slope throughout. So it's like a linear equation of y equals x, or y equals negative x.
Well, plus it's the only one.
I'm trying to catch up with you. So you're saying,
It's the only one that makes sense, right? Because if you look at there's one line of slopes that can be a linear line, and if you think of the equation, it's like y equals negative x. So
okay, wait, slowly. Y equals negative x. I know you've got something here. I'm just being dense.
So if you look at the same,
And if I don't get it, maybe other people don't either. So just say it again.
so there's in the very center, there's
Mhm.
a line that goes through as if equation y equals negative x.
Oh, okay. The slope is -1 through the center.
Yeah.
Yeah. Well, let's look at the equation and see why that would be. Y prime equals x plus y minus 1, right? So along the diagonal, x and y are the same, so, well, they're opposite, right? So they cancel, so the slope is always minus 1, yeah. I see that. Does everyone see that? If you look down the diagonal from upper left to lower right, all the little bars have slope -1. And if you look at number 5, you think about it, along that diagonal, x and y are always opposites. They cancel and you get -1. So, and there's no other one like that. Okay, good. All right. So now we're down to 4 and 6.
4 is 1.
4 is 1. Okay. So when I was doing it, like once you get 3, you know the fourth one. So 4 was the one that I didn't do. I just looked at it and it was the only one left. So what's the rationale that 4 is Roman numeral 1?
Well, let's just ignore the x for a second. You have 2 minus y, which means that as y increases, the amount that you're subtracting by increases, so the slope will get more negative as y increases.
So if something from top to bottom, the slope is getting bigger to smaller, then that could be the 1. And that's 1, right? If you look at the vertical lines, they all have a slope starting big and going to 0 at 0 and then getting, yeah, okay, that's good. All right, so we know that number 2 must be the sine times the sine. Anybody suggest something about that would... So you don't have to get into the meat of these things. You can just look at the little peripheral issues. Does anyone see something about 6 that matches only number 2?
Well, on the axes, where x or y are 0, that means the sine of one of them has to equal 0.
Now that's good, but that doesn't eliminate number 1 actually, because that's also true number 1. So, but hey, here's something. If you look up around, I guess it's at pi, at y equals pi, it levels off again. Or if you look along x equals pi, it levels off again too, which is not something that 1 does. Right. If this was a bigger graph, you'd actually see periodicity, right? Up and down and left and right. They just couldn't show you that. I guess to make it harder. Okay. You could try 7 and 8 because it might be fun. I mean, what would you do on number 2? You'd start at y equals 1, and you'd try and draw a little line that would kind of look like a sine wave, wouldn't it? Right? Well, I mean, like a sine wave curve, but not. It's more like a upside down cosine. Yeah, I don't really see that as all that beneficial. I put them down, but we're going to skip those. So, all right. Let me ask: is there any questions about direction fields? Again, they're a tool. If you actually had to construct one yourself, you could use it to kind of get a feel for what the solutions of the differential equation look like. But again, why would you do that if you have the technology to draw one of these things? There's something better to do. So, okay, again, any questions about this? So, if you're really observant back there, you might have noticed I wrote something up here. I wrote fuzzy direction fields, and I'm going to write under moderate Euler's method. Euler's method. I don't know how you would. I don't know how you would use Euler's method for anything but a first. Maybe you could, but a first degree differential equation. Someone remind me what a first degree differential equation is?
The largest derivative is of the first order.
Yeah. Now, it might be really useful if you had a nonlinear first degree, but we're not going to do that. We're going to use the same equation. Y prime equals x plus y. Now let me just explain Euler's method first. And we'll get into the geeky part. So with Euler's method, you've got a differential equation and you've got an initial condition. So we have y of 0 equals 1. So we have a starting point. And the idea is we want to know what happens to the curve in one direction or both directions. So we're going to pick some small value, some delta x, which I think the book likes 0.1. It's manageable. And you look at this point and you calculate its slope, which just happens to be 1. Actually, let me redraw. Here's 1, okay? And we'll just make believe these are tenths. And you calculate, you do a linear approximation. You say, if I go 0.1 in this direction, and this is a straight line, then I get to this point here. All right, what would that point be? Well, let's see how we would calculate that. So, first thing, we're going to use a linear approximation. So y equals mx plus b. That's our line. And we want to calculate first m. Well, m is easy to calculate. X plus y is y prime. That is the slope, dy dx. So from our first point, that's 1. Now we need to use this equation to find out from where we're starting what is b. So we know y is 1. X is now 0.1 over 0.1 times m, which is 0.1 times 1, plus b. So this is going to be, b is 9/10. Okay, so now we have our equation, y equals x plus 0.1, and we plug in 0.1, and we get y equals, no, that's not right. That's what I did wrong when I was doing this the first time. What do I have to do? Oh, I'm sorry. B equals 1 minus, no, that's right. What am I doing wrong? to start over here. All right, so we're starting at point 0, 1. And just do a whole chart here. X, Y, M, D. So X is 0, Y is 1. N is 1 because this is X plus Y. So we have 1 equals 1 times 0.1. Right? Oh, I'm sorry. All right. That's it. Now I got it. Okay, at this point, y equals 1 times 0 plus b. So b equals
1.
Yeah, what am I doing wrong here? Obviously, b has to be 1. That's the y-intercept. Oh. One more try here. y1 equals m1 times x, 0 plus b. So b equals 1. Okay, so that's my first approximation. Using the equation, I say y equals, now my next x is 0.1. So my next y will be 1 slope times 0.1 plus b, which is 1. So it's going to be 1.1. That doesn't sound right. One times 0.1. Oh yeah, that does make sense. Plus 1.1. Okay, so if I move over, this is now 1.1. All right, so I'm going to do this iteratively. So I'm just going to repeat these steps again. What is m now? Someone tell me what m is.
1.2.
1.2, right? Just x plus y. All right, so now I have to go through this trick again. I say y is 1.1, m is 1.2 times x, which is 0.1. Right, this is where I am now, plus b. So this is 1.1 equals 0.12 plus b, or 1.1 minus 0.1 minus 0.12.
0.98.
Okay, so thank you. 0.98 equals b. Now let's just try this one more time. So now we go to the next step, 0.2. And our equation is now y equals m, 1.2, 0.2, plus 0.98, 2.4 plus 0.98, no, 0.24 times 0.98 is 1.22, is that right? So now I have my next point. So the idea is you go a little step using a linear approximation, and then you correct it. You go another step and another step. would be extremely tedious. The book thinks it's worthwhile to have you do this kind of stuff. I think that's crazy. But the way we do these things today is with what?
Computer algebra system.
Some kind of, well, a computer, a calculator, right? So now we're back to, I was saying at the beginning of the class, I'm thinking a lot more in this class about the relationship of technology to what it is you learn. And this is not a computer programming class. I do not expect anyone to learn how to be a computer programmer. Or even, I don't expect anyone to do a computer program. However, I'm faced with, how do I explain this? So that's where we're headed. Again, some of you will have experience and you'll just say, oh, that was simple, and some of you will never seen anything like this. You don't need to worry that this will be on the final. But here we have a computer program, a very simple one that you don't need to understand anything about it at this point. We can go over it and explain what it does, and I hope this will be fun. Now you have the pressure off you. Awareness for the final. This is the kind of stuff that, take a computer programming class here. I'm sure you will find this really easy. Just out of curiosity, who here has some programming experience? I mean, okay, 1, 2, 3. Okay, that's fine. Don't panic. All right. So everyone take a look at this program. I'm going to explain a lot of things that you don't need to know. What I want to do is get past the stuff that's unimportant. If you look at the first 2 lines, they say include. To make this program work, it needs some capabilities that lots of programs need. The first line, like C.H, includes stuff if you want to print something to the screen. We're going to print something to the screen. And then the second line is useful if you're doing math. Actually, I don't even know if we need that. Yeah, we do need that here. The third line, int main, that's just how, this is a C program, everyone. This is how you start a C program. You started at the main, and this is where the computer's going to start doing work for you. This isn't very important for now, but you'll notice there are 2 things that say argc and argv, and that just has to do with how, when you type a program at a console, like if you, I guess if you've only used Windows or a Mac, you might you've only used a GUI interface, you might not know what a console is. So maybe I should, again, fire up some technology so you can kind of see what I mean by that. Let's see.
You want to use terminal? You can use terminal.
Yes. Bring up the terminal. Do I have to plug this in before I use? foolish of me, I don't actually have the program on this computer, but it would have been helpful. Come on in just a minute. Israel, I don't think you're going to have a real good view of it over there. Maybe if you move back a little bit. Okay, so on a Mac, you say terminal. On a Windows machine, you can say CMD command. Oh, we already got something running here. Sorry. Okay, so this is a console. There, because it's Unix underneath, you type in Unix commands. So the Unix version of dir, directory, is ls, and it tells you I've got applications, development, downloads, movies, etc. Or you can say find, and it'll list all the files that are listed here. Okay, I don't want this to get too mucked up in computer stuff, but okay, so getting back to the program, you'll notice the next set of lines say things like double and int. And in this particular programming language, you have to tell the computer beforehand what kind of variables you want to use. These are, you could think of them just like algebraic x's and y's. What double has to do with is, years and years ago, we used to have a type called real, meaning a real number, meaning a number that could have a decimal. And then that, later on, they changed that to float, as in a floating point. And double is shorthand for a double floating point. It's just, an accurate number that the computer stores. It can have probably about 15 decimal points, and then it's not infinitely accurate. So I've created a few variables. You notice I'm using x and y up here. I have two versions, x1, y1, x2, y2. Instead of a delta x, I have dx. And then I have my variables m and b, which I'm going to use. And then following that, int as an integer, numbers like 0 and -6 and 7. And I've got two of them I'm going to use, n and I. And you'll see how I'm going to use these here. The next line, you see //. // means it's a comment. It means it's not programming language. It's just a message to you to say what I'm doing. And so I say, print out a nice usage message. That means if I type in this program, which I call Euler, and I don't give it parameters, the program says, oh, you didn't give me any parameters, and then you can see over there, use Euler, and it wants you to type in x1 and y1, the starting x values, starting x and y values, dx, how much you want me to go each time, and then n, meaning how many times you want me to iterate. And then the thing after that, the \n, don't learn that yet. It has something to do with the C language. It's not important.
Next line. Line.
Yes, it means new line, yes. Why does it mean new line? I don't want to get into that. And then, and actually, if you don't give it parameters, it exits. It doesn't do anything. Okay, the next, then you see a little comment, initialize variables from input parameters. And you see a bunch of lines that say x1, y1, a to f, alpha to float. When you type something in, you're putting in an alpha letters, and it's going to convert those parameters. That's what the argv stuff is. So you can get started. and you put in those four numbers, x, y, dx, and n. And then finally, it just prints out a little message so you can see what you put in, starting at this number. Don't try and understand how it gets there, but it just prints out a little message. Right, now we're at the real guts here. And you see the word for. For is computer language for loop. I want you to loop here. You notice there's a curly bracket at the top, and then there's one further down at the bottom. And it's saying everything within these curly brackets I'm going to do a bunch of times. And inside the for loop, again, is a little computer jargon. It says, set the variable I to 0, and as long as I is less than n, the value, you said how many times you want to do it, that I++ is shorthand for add 1 to I. So he's going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if you asked it to do it 10 times. Okay, so now we're really at the guts. So here's actually the point where if you want to know what's going on here, you really want to pay attention. First thing I do, print current point. I just print out a little message saying this is where we are. It's going to print out a 0 parentheses 0 comma 1. Just going to tell us where we are in the loop. And should we call it the suicide prevention line now? It's sad. Okay. The next statement, this is in a computer how we calculate something, how we do a computation. We say m, that's the variable we want to hold the value of the computation, equals, and then we have some mathematical expression. So we have two variables, x1 and y1, which are holding the current point. We want to find the slope. Like I did on the board, you add together, you get m. Now, we're kind of, in the computer, we're juggling things. There's the current point, and we're trying to find the next point. So you can see right here, the next x is just the original x plus dx. So if I start at x0, my dx is 0.1, the first time through the loop, x2 becomes 0.1. And then, the next time through, you'll see it's going to be 0.2, 0.3, 0.4. Just going to kind of, go up the list here. The next thing we do is we calculate b, just the way we did on the board. Again, it's just a mathematical expression to calculate the current b value for that y equals mx plus b equation, that linear approximation. And then the final kind of statement there, we calculate y2 using y equals mx plus b, using that m and that b we just gave it, and the new x2. The last two lines, since we're going in a loop, we're starting with x1 and y1, and you're calculating x2 and y2. Well, at the end of the loop, we have to put the y2 and the x1 into the 2's into the 1's, so we can start over. And, okay, now, keep in mind, I'm not trying to teach you programming here. You already know how to do programming. You probably know what this is all about. If you don't, it's okay if you're not, quite sure. The main thing you should take from this is I've got a program, and it's just kind of what I was doing here in a loop. I'm telling the computer, I'm giving it instructions on how to do it, and I'm also telling it to print it out so I can see it. All right? So, we've done that. Yes, this is it's going to come in handy now. So I want to show you the results of this program. So in all cases, I ran the program starting at 0, 1. And the first time through, I just used this exact program. And you can see here, 0, 1 is my first point. Second point, I think we calculated up here. And then beyond that, we kind of find these different values. The x's are always going to be updated 0.1 at a time, and then the y that's the function value. So this is using a very small dx. Now the nice thing about a computer program in computers is once you get the code right, it does all the work for you. So it'd probably take us 10 minutes to do all this here and actually get it right, and the computer just does it instantly. The second box here, I modified the program a little. Really, all I had to do was tell it, don't print every line, because then this time, instead of using 0.1, I use 0.01. And I don't show you all the intermediate calculation because that would be 100 lines. And then next one, 1,000 lines, and then 10,000. But if you look down here, you'll see the numbers are all slightly different. And if we look way down here, you can see that when we get to the bottom, this more accurate answer, it's about 1% off. Here we have 4.07, here we have 4.4. So that's maybe a little more like 3% off. So we made the calculation more accurate. It didn't take the computer any seriously more amount of time. The computer did it pretty instantaneously, but we got a more accurate answer. And then we move on here. Again, now so the first line we're doing 10 calculations, and we're doing 100. Now we're doing 1,000 in the third line. We're using 0.001. And now you can see the difference between these two is now less than 1%. It's about 0.09% difference. 4.40 and 4.43. You can kind of go, wait a minute, why are we wasting any time with these intermediate results? I just want to show you kind of the progression here. And now, the last time I tried this, okay, so the number here is 4.439, 4.36. So we're talking about 0.3% difference. We're honing in on, now these are all approximations. But the computer, you can just dial in whatever precision you want. It's not going to give you the exact value. It's going to give you a very good value. And quite honestly, if you were doing a scientific project and you wanted to find this out, well, you wouldn't do these intermediate steps. You probably wouldn't do 0.0001. You probably just cut dx down as low as the precision involved, which is probably 10 to the negative 11th or 10 to the negative 12th. And you would get a really very accurate, probably accurate to 10 digits value for this function. So that's the kind of computer side of this. Any questions about this?
Can I ask you a programming question?
Of course.
So I'm more proficient in Java than C, but it seems to me that the languages are pretty similar.
The computational stuff is pretty
Right.
much identical, yes. The outer structure is a little different.
Yeah, I can understand pretty much every single line of code here. The one I have a question on is like when your parameters, when you're declaring the main method, when it says character ** RV, is that like the equivalent of an array in Java?
That's a pointer to an array.
Okay.
It's just the way you start C programs. It gives you a pointer to an array, and the array has the parameters in it as text. It's a text string parameter.
Got
Yeah, you don't have, because you do have some pointers in Java, but they're pointers to objects.
it. Right.
Here you can have a pointer to anything. And, if you make an error, it crashes the program. It used to crash the computer, but now the operating system prevents that. So, yeah, okay. Okay, so let me tell you about a little thing I cooked up. Let's see here. Let's go back to the computer for a second. Let's go to my website. My picture there. Yeah. Oh,
That's fine.
please don't memorize my secret identity. Okay, there we are. Assignments. Okay, so down here, can you see where my wiggling pointer? I don't know. Well, number 15 is the assignment that you couldn't see. You're supposed to be able to see, but you couldn't. So that's the only real homework. You can get that in whenever. Notice 6. Star, 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 optional, star, star, star. Optional, everybody understands what optional means. You don't have to do it. It doesn't count against you. If you do it, you will get some extra credit. Okay, rules for this assignment. Okay, so if you look on page 507. Okay, 507.25 says, program a calculator or a computer to use Euler's method to compute y1 where yx is a solution of the initial value problem. It's kind of ugly looking, but it's, the method we talked about will work. And everybody should probably do B, but I don't care. And then find the errors in Euler's method. So that's one computer problem. And then 26, notice it says 26A. B says check your work by using the CAS. I don't know what the CAS is, to draw the solution for.
Computer algebra system, you can use mathematics.
Well, yeah, you can use, you don't have to do B. I'm not asking for that. So there are 2 computer programs involved, and here's what the assignment looks like here. You may work on this in groups of up to 3. You could kind of form a little corporation here and work together. That's fine. I leave it to the group to ensure that 2 people don't do the work and the 3rd person hangs on, but you should all work on it together, and you should all, you can bring different skills to it. We'll talk about that. People who aren't programmers, I don't expect to do computer programming, but you should understand the algorithm, and you should attempt to understand how the program implements that algorithm. You may even enlist an outside person to do the programming. You should be explicit about that if you do that. As long as you come up with the algorithm or rhythms yourself. I'd like you to, this is like a little paper, you're going to write, this is what we did, this is who worked together, this is the algorithm we used, this is what we iterated, and I want to see the source code unless you do it on a calculator. If you do it on a calculator, okay, calculator. You would have to learn how to do this. I kind of half-assed know how to do this, but I wouldn't want to do it this way. You hit program. All right. Go back. So you hit this program key, and all of a sudden you can execute, edit, or create a new program. And you would have to look up in the manual, and maybe you already know how to do this. But what I would want from you, if you decide to do it with a calculator, because this calculator is perfectly capable of doing this iterative thing, I would want you to take a picture of it and email me a picture of the program so I can see what you did. Because otherwise, how would I know?
Could hand you the calculator.
Sorry?
Could hand you the calculator.
Yeah, and that would cause me grief beyond belief. You go, oops, I erased it, I'm sorry. Okay, let's see what else do I see. So it says it all this here, either a screen dump. Oh, if you have a simulator, they have simulators, right? You run this on your computer, and then you can do a screen dump. You do an image of the thing. You still have to send it to me. Okay. Was I not clear the first time? Note, this is optional for extra credit. No deficit to your grade will occur if you decide not to do this. Purely as like a project for science class or economics. You know what? I had some second thoughts about it. You must turn it in at the beginning of the class. That's a week from now. No. You know what? Turn it in by the final. You turn it in before, turn it in by the final. That's okay. If you want to do this. I think this is a fun project. If you don't know anything about computers, you might learn a little. If you already do, I should probably restrict you from doing this and tell you, no, you're too smart already. But no, this is cool. We're going to solve some differential equations iteratively, if you do this, the way I did, over here. So again, also there are people not in class. If you want to explain to them the rules, they can work on it too. All right. Any other question? Any questions about this project? It's not going to make. Well, I guess it could. I think I'm assigning up to 2 points, 3 points on top of your grade. So that could make the difference between a grade, if you want to do it. Okay. All right. We're going to take a break, and then we're going to come back. This fuzzy. This gives you not a perfect answer, but pretty much as accurate as you want. And then we're going to look at the exact answer. So. Have a little walk. That question. Which one? Well, I'm going to try and come up with a question, but you don't need to turn it in. Okay, thank you. What can you say about the graph of the solution to the equation x prime equals x, y prime equals x times y cubed when it is close to 0?
So I know that the y prime would, as x approaches 0, y prime would be 0.
Okay.
But when it approaches infinity or like a really large number, it would be a really large number in this image.
Well,
Because,
so y prime is x times y cubed.
So you find the answer. No.
No, you gotta think about this. So, if x is large, right, it could be, what if y is very small? Then it's still not gonna be that large, right? It's still, I mean, it's still gonna be, it's not gonna be as large, but it's gonna get bigger. And then derivative is gonna be that value, right? So as you go further, it's gonna get bigger, so it's just gonna,
Go to.
it's just gonna, yes, it's gonna go outside.
So what should I say as x of which is like a large number? What kind is just a large number?
I guess so, that would work.
And then I also need help with the rest of this question.
Okay.
I just don't get, there's like A, B, C, D.
Yes, I always wonder about signing such things.
Yeah, so if I don't get one of them, the rest of it's just kind of like,
Verify all members of the family are solutions. Well, that's just you plug it in and show that it's true,
okay, so.
right? As you find the derivative, remember I did this in class, find the derivative and then you plug this in
Okay.
to here and show that.
Okay.
Okay. All right, I'll be back in a couple minutes and then we'll do some sharp stuff. Sorry?
I had a question next.
Sure.
So, like, in this program that you showed us,
Mhm.
this line says n equals one plus y, like that's specifically referring to the example you showed us.
Exactly.
But you want us to have a general solution, right?
No, no. If you look in the book, they
Okay, it
give
gives
you
specific-
the
okay.
two specific problems. That's right.
All right.
Yeah, you can go ahead and do something general, but then you have to think of a way, how do you input the equation?
Right. Then I'll do that for 10 extra credit points.
If this were a differential equation class, I would be happy to oblige. But it's not. I think I'm probably overstepping my bounds here a little anyway. So. But we'll see what we can do. Okay. All right, is everybody focusing back from break? Okay, so differential equations are important in science and social sciences, and we know how you can get kind of a feel for what the solution might look like with a direction field, how you compute the answer if there's no direct way to solve one. Tuesday we looked at a differential equation and I just kind of threw a solution at you, but I didn't say where it came from. And today we're going to look at actually how you would solve some equations. I guess I want to just want to make a little underline here. I've described some categories here. So there's the degree of the differential equation. We looked at a second order. We're mostly going to look at first order. So, but there's no limit. I don't know of any third degree differential equations that come up in science, but there may be. There's also linear versus nonlinear. So what's that about? So if I have an equation like, say, a y double prime plus b y prime plus y equals c. This is linear because the function and its derivatives are multiplied by constants. You might want to think of a linear equation, which could be ax plus by equals c. That's a linear equation. But y equals x squared, it's not a linear equation.
So it's a sum of linear terms.
Yes, yes. This is not, this is. It's different terminology. I mean, here we would call this a second degree equation, right? But that's not, we don't use the same terminology in a differential equation. A nonlinear might be something like y prime equals xy. Because now we have y multiplied not by a constant, but by a function of x. So there's linear and nonlinear, and we're not going to run into these, but all the equations we're looking at are ordinary, which means there's really only one independent variable, x. If we had more, we had a differential equation where the solution is a function in, say, x and y, that would be a partial differential equation involving partial differentiation, something we haven't covered in this class. If you take the next class, I believe it will, calculus C, or maybe it's D, it will cover partial differentiation. But you know, we're not doing any of this. We're going to look at this today, and we kind of look at this. All right. We're going to start off with a linear first-degree equation. We're going to look at it in very general terms. Y prime of x plus some constant times y of x equals 0. And we're gonna try and solve this. So first we note that if we take the expression e to the ax, this is never equal to 0. Right? Can't be 0. So we can multiply both sides of this equation by this value without causing a problem. So we say e to the ax, y of x, plus a e to the ax, sorry, y prime, y of x, equals 0. Okay, now, it's hard to see where we're going forward, so I'm just going to write the next step, and you're going to look at it and think about how we would go backwards. Right? This is the derivative with respect to x of e to the ax times y of x. And then this is still 0. Why is this so? Well, think of the product rule. Product rule says the derivative of something times something, right? So e to the ax times the derivative of yx plus yx times the derivative of e to the ax. That's e to the ax times a. So if we find this derivative, we will get this expression. So these are equivalent. So if we now integrate both sides of the equation, on this side we get e to the ax times yx. On this side of the equation we just get some constant. So solving for y now, we find y, we want to divide by this, right? So this just becomes c e to the negative ax. Wow, it's pretty straightforward. We didn't do anything we didn't already know how to do. Okay, but of course, we might be interested in this, not just a general solution, but for a specific solution. So if we start at some point x naught, y of x naught equals y naught. As we have some starting condition, we can plug this in, right? We can say this is equal to c e to the minus a x naught. which means that c is equal to y naught e to the a x naught. I just multiply by e to the ax naught here on both sides. And that tells me that given this initial condition, this is my c, and then my final solution becomes y of x equals c, which we now know to be y naught e to the ax naught times e to the minus ax naught. E to the minus ax. So this just becomes ax naught minus x. So now whenever you see this linear first degree equation, if this is the starting condition, you know this is the solution. It's like the quadratic equation. If you memorize it, you can always use it. I'm not suggesting you memorize it. Okay, let's take an example. Just erase this incredible artwork here. You took pictures so that you can get it in the Museum of Modern Art, right? No, it's gone. All right, so what if we had the equation y naught of x plus 3y of x equals 0, and the starting condition is y of 1 equals pi. So what you want to see in your head is, here we have this differential equation. You kind of imagine the direction field as a bunch of arrows, and if you look at the place where y of 1 is pi, there's some curve through that. We're going to find that. Well, again, now we know the formula, so we know that y of x, I need to say this, x naught equals 1, y naught equals pi, right? So this is equal to pi e to the a is 3, x naught 1 minus x. And that's the solution. So that's an exact solution to a differential equation. Okay. Any questions about this? No. Okay. We're going to take this to the next level. Everybody done writing down they need to? I'm going to make this just a little bit more complicated. Now we're going to introduce, this is still a linear first degree equation, but now this is equal to some constant b. And we're going to try the same strategy. We're going to multiply both sides by e to the ax. I think I'm going to, for the moment, dispense with putting in the parentheses x. You just have to, whenever you see y now, you know that's a function, right? Y prime plus a y a e to the ax y, and that's equal to b e to the ax. So again, the same simplification works. This is still the derivative of e ax y, but now it's equal to b e to the ax. So when we integrate, here we get e ax y. Here we're going to get b over a e to the ax, again plus a constant. And then, again, by multiplying through by e to the minus ax, I'm going to get y of x equals b over a plus c e to the minus ax. So that's, again, a general solution for this slightly more complex equation. But again, we have some initial condition, y at some point equals some value. We can plug that in, get y naught equals e over a plus c e to the minus a x naught. And now we're going to solve for c. So c is y naught minus e over a times e to the minus a x naught. And that being the case, we can write down the general solution at a with specific initial conditions. It's just equal to e over a, this comes from here, right? E over a plus c, which is now this elaborate constant, times, well, again, I'm just going to simplify it. This is just a x naught minus x. Okay, so this, of course, this works also for the original equation if you just plug in b0. This simplifies to the previous equation. Let's try an example. We have y prime of x minus 1/2 y of x equals 1. So here's my a, here's my b, and my starting condition is y of 1/2 equals minus 2. This is my x naught, and that's my y naught. Well, here we have a formula. So we want b over a. So 1 over negative 1/2 is negative 2 plus y naught, which is minus 2 minus b over a. Just being careful here. Times e to the a, which is minus 1/2 x naught, 1/2 minus x. It's not the solution I was expecting. Take a look. Something wrong here? suppose that's, so y of x equals, this is negative 4 minus 2, so negative 2, I'm sorry. That's not right. Minus 2. Oh, no, I certainly did something wrong here. Take another look. Oh. I'm going to try one more time. Doesn't seem like I've messed myself up on the simple stuff. That's the way it usually works. Okay, so b is 1 over negative 1/2 plus y naught, which is negative 2 minus 1 over negative 1/2. Yay. There's a 1/2 minus x. So if this keeps coming out to be 0, and the derivative of 0 minus half of 0 is definitely not 1. Well, I'll just have to think about that for a minute. Anybody see my error? How embarrassing. Well, there's obviously something I'm doing wrong here. I'm just not quite sure what it is.
Maybe you copied the problem down wrong. Like, are you sure that y naught's supposed to be negative?
Well, I'm willing to entertain that possibility. However, I think actually that's probably the case. But you see, what I'm distressed about is that it doesn't really matter. I should still get the right answer. In other words, if my initial condition is y of 1/2 equals minus 2, and I plug it in, I should still get for, see, if the result is it's 0, y is 0, then this equation should still be good, and it's not. Well, let's try your idea. Maybe this should be a plus, right? So this becomes so this becomes 2 plus oh, wait a minute. Okay. I think I'm doing something that students do all the time. Just can't see the forest for the trees. What's 2 minus 2? It's not 0.
It's 4.
It's
No,
4.
But you said that, why not just negative 2 and not 2?
Oh. You're right. Okay, let's go back to the other strategy. Okay. This is plus
Negative 2
-2
plus
plus
1 over 1. Or you could do minus negative.
and then this becomes a is
Negative.
1/2
Oh,
x
Oh,
naught,
1/2.
which is 1/2 minus x. Okay. So this is 2 plus. Wait a minute. Why did I get 0 again?
And I think that should actually be, it should be minus, because it's y naught minus b over a, and then a is positive, so,
Oh, you mean like that?
right.
So this should be 2. That should be minus 4. E to the 1/2 minus x. Is that what you're saying?
Yeah.
Yeah, that's not the right answer either.
What is the answer?
The answer is supposed to have a -3.
Are you sure that answer's right?
No,
No, your answer?
I'm all bets are off here. I gotta say, this is more fun when things go smoothly. Okay, so I think this was the original problem. And I think it should have an answer. So let me just break this all down. So A equals minus 1/2, and B equals 1, and x naught equals 1/2, and y naught equals minus 2. So let me just plug everything in. So 1 over -1/2 plus -2 minus 1 over 1/2 e to the -1/2 x naught is 1/2 minus x. Good. Okay. So this is -2 plus
Still get 0.
0. Oh, wait. Wait, that looks like, that is a solution. I'm sure it's the wrong problem, but it is a correct solution, right? So if this is y, right, y prime is what? 0. So if you plug it in, of course, -2 times -1/2 is 1 equals 1. Oh, okay, so that is a solution. I wrote the problem down wrong. Okay, I'm happy now, because when I don't remember something, that's just me being stupid, but when math doesn't work, the whole world falls apart. atoms, go flying off into nowhere. Okay. Well, that's actually it's a teachable moment I just threw away. That's what they call an equilibrium solution, right? Okay. So, what little tweak could I do to make
A 1/3.
Wait a minute. On my page, I see y of a half equals, I think that's what it should be. Okay. Threw me. All right, let's try it again. Carefully. A equals minus a half. B equals 1. X naught equals a half. And y naught equals minus 3. Crossing my fingers here. So B over A is -2 plus -3 minus -2. Still not coming out right. It's closer. So this is -2 minus e to the -1/2. Well, these are still good solutions. We could try this one if you want. Let's see. So if we plug in a half, this has to be -3.
That works, because you have -2, and then,
But the formula's not right. I mean, if this is the, forget that part, but I'm expecting a -3, so I plug in a half, that's 0.
and then e to the 0 is 1.
Oh, -1. Oh, okay, so it is still, so it's a correct solution, it's just not the one I expected. So I just don't remember, I didn't write down the problem right. That's terrible, but that's what happened. Whoop. All righty. So the formula is correct. The teacher is brain dead, but the formula is correct. Okay. That was fun, wasn't it? We now have a absolute solution to the linear first degree, right? Is everybody on board with what that means? Okay.
Wait,
It's just the example. Here.
is it online?
No.
Because he miswrote it.
Maybe I'll put it on the line.
Okay.
Here, just write down the problem and solve it. Now you should be able to. Tell me when you've written it down. I can erase it.
I wrote the wrong one.
All right, I'll write the right problem and I'll.
Okay, I wrote it down. Oh, okay, well, you erased
All right,
it.
you got all this done now, right? All right. See, here's where we. I hate to make people uncomfortable, but I hate to make them comfortable. So if I say this will not be on the final, then some people just zone out. That's sad. But I think this is the coolest part of differential equations. I don't know if that will help. So now what we want to do is we want to go from linear, we're not going to do these. We want to solve the first order nonlinear equation. We want to solve it. we want to have a solution. So let me show you what that looks like. This is what the equation looks like. And now, y is no longer multiplied by a constant. It's multiplied by some function of x, which we're going to call p. I think I'm going to leave the x's in this time. And worse yet, it's equal to some function of x. So imagine here like just x or x squared, or this is, y, it's not y because the y's are here, but this could be some other function of x, the square root of x. All right, so to solve this, we have to do a little work. The first thing is we're going to define a new function, h of x, which we define as the integral from x naught. This is going to be the x naught for our starting condition, but you don't know that yet. And we're going to integrate p from x naught to x. You should all recognize this. This is one version of the fundamental theorem of calculus. We're not really saying anything, well, here's the fundamental theorem of calculus here. The derivative of this is p of x, right? Okay, now we're going to go crazy. Before we multiplied this by e to the ax, where a is this coefficient. Now we're going to multiply it by e raised to the function that we just defined here, h of x. This little magic function we create here, whose derivative is p of x, we multiply through by that. And now we're going to take the same step we've been taking all along here. We're going to recognize that the derivative of e to the h of x times y, if we use the product rule on this, what do we get? We get e to the h of x times y prime plus y times the derivative of e to the h of x. What's the derivative of e to the h of x? It's e to the h of x times the derivative of h of x, which is our friend e of x. So these two are equivalent. This is just you go from here using the chain rule, you will get this. And that's still q of x e to the h of x. Well, what are we going to do here? Of course, we're just going to find the integral. And in particular, we're going to, this is awkward to write it, but integrate from x naught to x. So on the left side, the integration undoes the differentiation. We have e to the h of x, y of x equals this. Well, we're going to end up with this integral but as part of the integration we end up with a constant. So again, we multiply through I guess we don't have to introduce that constant like yet, because we've still got an integral here to do. Okay, so multiplying through by e to the minus h of x, now we've isolated our function. E minus h of x times this integral. Note that use a different dummy variable. That's what I wanted to do before. Notice that I may not be able to find an integral here, right? But if I can, I can solve this completely. If I can't do this exactly, maybe I can use a computational method in the end. Okay, so there's not enough room on this board here, but again, we're going to introduce a starting condition. So y of x naught is the same x naught as here, equals y naught. And we're going to plug it in. So okay, so first, so y of x naught equals e to the negative h of x naught times integral x naught to x of q of s h of s ds. And now I want you to look back at the definition of h of x. Right? So, so this is e to the integral of x naught to x naught p of t dt. So what is this integral compute to?
E to the same thing.
It is 0.
It's 0, right? We're going from x naught to x naught.
Oh.
So this is 0, and so this is 1. Well, that was a nice simplification. I'm not even going to write the 1. I'm not even going to write this. I'm just going to say equals 1. Okay, so now we're left with integral from x naught to x of q of s e to the h of s ds and that's equal to y naught. Oh, plus c. And that's equal to y naught. Oh, but again here we have, right, we're plugging in for x naught. So what happens to this guy? 0. So we end up with c equals y naught. So finally, we're going to write our final solution. So to this original equation, this nonlinear equation, we don't even know what px and qx are, but we know this is a solution. It's e to the minus h of x integrated, times, yeah, I left out that c. So c is y naught, so this is just y naught plus this integral from x naught to x of q h of s ds. Okay, now again, keep in mind we don't know what q of s is. We know h of x is this integral over p, but we don't know what p is. So this is it's unclear whether we're going to be able to do this. But we do know we described a function that solves this differential equation with starting conditions, y of x naught equals y naught. So that is a huge, huge accomplishment. I have time for a problem. Okay, so what if our actual equation was y prime of x plus 2 y of x, that's my p of x equals 2, right? Equals x squared, meaning my q of x, which is x squared. Well, first let's find what h of x is. H of x is the integral from x naught. Oh, we want the initial condition. Y of 0 equals 1, right? So x naught is 0 to x of p of x, which is just plain old 2. Doesn't matter what the dummy here is. So this is equal to 2x. So writing down our solution now, y of x. See, here's a case where the integration is easy and it's going to work. So e to the h, negative h, which is negative 2x, times y naught is 1 plus the integral from 0 to x of now q of s, which is just s squared e to the 2s ds. All right. Now we're on pretty firm ground here. This is not we've done this. How do we do this integral? What's the technique?
Integration by parts.
Integration by parts. I'm just going to write this down. You can, those of you who are skeptical, can do this for as a homework problem. Somehow I feel there's not going to be too much skepticism here. This is e to the 2x, 1/2 x squared, minus 1/2 x, plus 1/4, minus 1/4. And so we just plug that in here, and y of x equals e to the minus 2x, 1 plus, repeating all that. I'm not going to repeat it. We don't have time. All right. In conclusion, we're going to go back and use this on, I think, on the, what's the name of that equation? threw at us early on. The logistic equation. We're going to throw this solution at the logistic equation, and we'll learn a little bit more before we're done. Okay, there's no homework on this stuff. You could finish up the homework from last week that I didn't post. And if you want to work on that computer thing, knock yourselves out. I mean that in a positive way. I think this is a place where teaching of calculus has to go. It's kind of unavoidable that if we're going to try and show you numerical methods, you at least have to admit that computers should be involved. All right, thank you. I'll be around for a few minutes if you have questions.